A little bit about us. AEC is an international trade association dedicated to providing information and education about aluminum extrusion and its processes. Can you go to the next? Hydro Aluminum Metals USA is headquartered in Baltimore, Maryland. This U.S. division of Hydro supplies aluminum billet, the feedstock for extrusions, to their own plants, as well as other aluminum extruders across the country. The company performs casting of aluminum billet at 2 U.S. locations. EXCO is one of the largest producers of extrusion tooling globally. It has 5 state-of-the-art manufacturing facilities, including Markham, Ontario, Canada, and the company's primary mission is to provide dies which will produce quality product with maximum speed and efficiency, primarily by designs that ease the extrusion process and assure long operating life. Next. Today's webinar is Introduction to Extrusion Dies, and it's presented by Richard Dickson of Hydro Aluminum Metals USA and Rick Liscomb of EXCO Canada. Richard Dickson is Director of Customer Training and Development with Hydro Aluminum Metals USA. He has more than 30 years experience in the aluminum extrusion business. Richard is an active member of the AEC's Die Committee and the ET Seminar Committee, which directs the program for the longest running aluminum extrusion technical conference, the International Aluminum Extrusion Technology Seminar. He also serves on several Aluminum Association and ASTM technical committees. Richard is the editor and co-author of Hydro's Die Design and Manufacturing Manuals. As leader of Hydro's International Die Team, for many years he drove the effort to create and/or refine ever more productive die designs. Richard's passions remain advancing extrusion beyond its current limits through understanding and education. Combining extrusion and die design with the former Alcan, now Rio Tinto, and EXCO, a global designer and manufacturer of dies, Rick Liscomb has been part of the aluminum extrusion industry for 40 years. He has held various positions from janitorial through to upper management. The die side of his career has ranged from production design through to many die development teams. Rick has also been an active member of the AEC and has served on AEC and ET seminar committees. So before we begin, I have some reminders. All computer and audio telephone lines are muted, so if you have a question during the webinar, please select Q&A or chat from the toolbar. Type your question in the dialog box and our presenter will address your question at the end of the presentation. Also, as a note, we had a little bit of technical difficulties with our land phone line, so our speakers are on their cell phones, so please forgive us for any audio issues. We are recording this presentation and we'll send a link once it is posted. And also the slides for today's webinar will be available following the presentation. Also, we'll send you an email with a link to a survey about today's presentation, and we ask that you take a moment to answer the brief survey. Now, it brings me pleasure to turn over the presentation to our speakers for today's webinar, Richard Dickson and Rick Liscomb. Gentlemen, take it away.
Good morning and welcome aboard. It's a pleasure to be here with you folks.
Good morning to everybody. Just like to point out, as Nancy said, we had a small technical difficulty here. All the phone landlines in the area went down 10 minutes ago. So we're going via our cell phones. We hope this is clear enough for you to be able to hear. Let's get started. Extrusion is a process by which we put through a steel, usually H13 die, to produce a finished extrusion shape. This involves a lot of pressure. There's a lot of pressure necessary to physically push that billet through what is a relatively small hole. And also the aluminum has to be hot. it's beginning to approach its melting point, and one of the restrictions we have on extrusion is that once all the work has been done, pushing the aluminum through the die, we mustn't have it melting when it comes out. And Rick is going to talk a little bit more about that in a second. Now, one of the questions, I guess, you're end users of extrusion. One of the questions about extrusion is always, why do we do it? And why extrusion? Well, if you look at the top left picture there, there is a graphical representation of the same shape made by a rolling form sheet. So by forming a sheet into a shape and by making it with extrusion. The roll forming process and the dies needed are very expensive to set up, and it really doesn't allow the full 3D creativity of the designer to come through. Extrusion, meanwhile, is a relatively cheap initial setup cost. The die can be just a few $1,000s, and you can have a prototype on your desk within a week or so. So much quicker, much simpler than roll forming. But its great strength is it allows you, the end user, the architect or the engineer, and people out there in the industry using extrusions to use your full three-dimensional creativity. You can use wall thickness variations in the aluminum to put strength where you want strength. You can see here in the bottom right-hand corner of this slide is a picture of a fairly complicated section, but we have put mass in the section where we want it and thinned the walls where we don't want it. This means that we can get a structurally strong component out, but for minimum weight. Not only are you benefiting from the weight reduction of the aluminum over other metals, you also have the ability that you're not using too much where you don't need it. It can also open up your creativity. Here is a group of extrusions which have been designed to all slip together. Drilling a few screw holes means that you can make a very, very strong, structurally sound component from interlocking extrusions. And this, again, it reinforces the ability of the end user to use three-dimensional creativity to produce the end product. And aluminum also can be joined in many ways: mechanical, adhesive, bonding, and welding. So there are many ways to bring these structures together, and it really frees up the creativity of the end user. Let me show a small couple of examples here. The first one in the top left are 3 extrusions, and you can see how they interlock together to make a hinge. That's one particular use, and that hinge can be put into the exact end-use position, screws driven into those screw lugs, and the finished component is made. Alternatively, the one at the bottom is showing making a channel for running cables, which is in an automotive structure. Instead of drawing the cables through a tube, what we do is lay the cables and then clamp the top piece down on. It clips into place, and lo and behold, we have a cable duct with the cables in, reduced production manufacturing time for the finished components, and total functionality.
So as we can see, the world of extrusion is changing more and more. Back in the old days when it was rod and bar, we had one system to use. Today that we're getting into more complex shapes, we really have to start changing our attitude and communication skill or patterns or paths to the way the order is being placed. But traditionally, what's a customer want? Well, a customer goes up and gets a purchasing manager to call the extruder and normally has a shape that's tolerance and requires the customer, gives the customer the product that he wants to end with. Then over and above that, the properties and the surface finish also become a bit of a discussing point as to what's exposed, what isn't, and possibly they want close tolerance and special surface tolerances. Well, the problem is today, when we get people ordering the tooling and it's an out of standard tool, then there isn't a possibility to communicate and improve it for both sides. So really, what's a customer buy? Well, essentially what the customer is doing is renting the press time and the expertise of the extruder. So difficult shapes extrude more slowly. The more complex they are, the slower it can be. The more slowly they run, the more time it requires. As we start to build in this complexity, we realize that the cost of the extrusion has to vary because the extruder has to be able to pay for his equipment, and nobody wants your supplier to go broke. So understanding what we can do to improve the productivity of a shape becomes a very important step in today's shapes. So this webinar is going to cover as much as we can in 45 minutes. But as you can tell, that will be a limited amount. Now, if perchance there's a lot of interest and want some additional information, Richard and I would be willing to do another one that would get into more specifics and gladly see what we can tackle and help anybody with. But if we take a look at these particular shapes, and none of them are complex extrusions, but they bring into your mind what the subjects are we're going to be covering today. Where we have semi-hollow shapes, we have hollows, we have multi-void mandrels, and we have solid dies, which are the simplest of the bunch. But before we can get into determining which is easy and which is the complex ones, we have to know a little bit more about the dies and the problems that come about by extruding some of these non-standard type of shapes. To do that, we have to realize that a steel looks really strong and aluminum looks really soft. But the truth is, it takes a lot of pressure to push the aluminum through the die because of the reduction ratio from this very large diameter log to the small, thin, expected shape coming out the other end. Well, when we take a look at this and we realize that the loads and temperatures that are involved, it's a different type of beast once we just to get into that, and most people don't realize just how much of a variation there is. But if we understand that extrusion is like a tube of toothpaste. If you picture a tube of toothpaste, you put some pressure on the end of the tube and a round rod will come out onto your toothbrush. If we change the configuration of the hole in the end of the toothpaste, it would come out to whatever product it is we want. So within the process itself, as stated earlier, we have things like solid dies, which are relatively simple with much lower tooling costs. And then we have hollow dies, which comprise a lot more complexity and just the flow patterns themselves, and the tooling costs, of course, are higher. So when we turn around and we look at these solid profiles, what we see is the extrusion direction will be from top to bottom. The aluminum goes through the die aperture. Where it's going through that aperture, it's actually rubbing on what's called bearing, which is what controls the velocity, because aluminum loves to stick to steel. So that frictional work actually controls the velocity of different apertures or different size apertures within the steel itself. And that essentially is what you end up with, a solid shape. When you turn around and you look at hollow profiles, the dies become much more complex, as in it's a three-step operation. The material must go through the ports. It goes down along the what we call bridges, what suspends the mandrel. The material actually meets together in a welding chamber prior to the aperture. It adheres to itself, and then it extrudes out over the mandrel that's suspended and the die plate which forms the outside portion of the shape, both sides having bearing, and then it extrudes out and you end up with a hollow section, and the open part in the center being relatively any configuration you want, but it does take a slower extrusion speed and a lot more pressure.
And as Rick says, there's a lot of work going on here. The metal goes over the web, through the ports, then it's joined together again under the bridge and arm, and then it goes through another die plate, which has got the mandrel on the outside. So you're starting out with an 8 or 10 inch diameter billet, and you're squeezing it through these small holes, and it takes an amazingly large amount of force. I guess most people have at some stage in their life iced a cake. And you'll notice when you're making the big stars that look like Hershey's Kisses, it's easy to squeeze the bag. When you're making the fine piping which says happy birthday daughter or happy birthday mum or whatever it is, you have to squeeze the bag a lot harder. And extrusion's the same. The smaller the shape you're squeezing down into, the more force you need to apply. So what I want to do is I want to give you an idea of the forces that are involved, because we have to set the environment in which the die lives. The die, as we've said, is loaded very close to its yield strength, to its breaking point. It's hot. The aluminum is up in the 800s. The die is in the 800s Fahrenheit. And the pressures can be enormous. And I'd like to look at the loads on this die in extrusion so you can understand some of the challenges. Rick will then take this into some practical implications in some extruded sections. But let's look at a press that extrudes a 10-inch billet. One of these presses normally needs about 3,500 tons of hydraulic force available to be able to push aluminum through the dies. And also it has to be pushed through the container, so there's a lot of work got to be done. That is 7.7 million pounds of force being applied to this process. So I want you to get an idea of the scale. And to really bring it into something which we can feel rather than just hear. If we consider a base model Toyota Tundra V6 truck, that truck weighs about 2 tons and it's about 19 foot long. So if I want 3,500 tons of Toyota Tundras, then I am going to have a traffic jam of 5.7 miles of Toyota Tundras. Now, for those that you live in the big cities, I guess that's something you can be accustomed to. But what I want you to do is to mentally envisage 5.7 miles of V6 Toyota Tundra trucks bumper to bumper. Now, let's put them on their ends, sitting on a 14 to 15 inch sheet of steel. That is a lot of force. 5.7 miles is 33,250 feet. That means that that stack of Toyota Tundras that you can see there are actually a hazard to aircraft in cruise. That's how high it is. So now, in your mind's eye, think of that crisp morning when you've looked up and seen the contrails of aircraft flying at altitude over you. Now imagine a stack of Toyota Tundra trucks that go all the way up to those contrails. This is an enormous load, and it's all sitting on a 14-inch disc of steel. The end that's pushing, the stem that's pushing, that 3,500 tons is actually nearly 100,000 psi of pressure. We're actually loading the stem which is pushing the system to almost its limits as well. So extrusion is operating very close to the operating limits of many of the components. We're pushing the system as hard as we can to get the most complex and thin-walled sections we can. So behind the tooling, oh dear, this is moving slowly. It will get there in a moment. There we are. If we imagine this stack of Toyota Tundras sitting on top of the die on its own, a simple 1-inch, 2-inch sheet of H13 steel just is not strong enough to take this load. We put what's called support tooling behind it.
Just to realize, I'm sorry to interrupt here for a second, but it's very important that we realize that these dies are made out of steel called H13. H13, the H stands for hot work. If the temperature is not controlled properly on this steel, then it's not really the best steel for this situation. But because it's continually being introduced to heat, it has the ability to be able to deflect and come back nicely without breaking.
So this steel is pretty good for this purpose. And even though it's extremely strong steel, it requires support. I'm going to try and make a mouse appear on the screen. And the part the mouse is pointing at now, the brown area, is the back die. This is a method of keeping costs down. The tool stack has to be a fixed size, and we don't want to make the whole die with a complex manufacturing process. So we make a thing called a backer, and I'll show that in another view in a moment. Those fit inside a die ring. This die ring is also an opportunity for us to use slightly smaller diameters, so less steel where appropriate, and give us the facility to use larger pieces of steel where we need it. So this gives us some flexibility in the cost of the tooling, depending on the shape we're working on. And all this sits on this kind of purpley area. I'm just getting my mouse in there. There we are. And there, this is the bolster. The role of the bolster is to transmit the force from the die and the tool stack, the bolster is part of the tool stack, into the press itself. And the press itself there is the platen ring where the extrusion comes out of the press. The reason I'm showing you all this and wanting to talk about trucks and things is I want you to understand the load on the tool stack is very high. It is very close. In many cases, the dies are loaded to close to their yield. And since we want the die to be the same size after extrusion as before to use again, we don't want to yield the die. Now, Ricky's going to talk to you about some elements of the design, such as tongues and screw lugs and things that you all want out there to make your sections work perfectly. But they become challenges because these loads are so high. I would like $1 for every customer that said to me over the years, "Oh, but this is tool steel, you can't break that." I have seen boxes and cases of broken dies where people have been a little over adventurous. So it is possible to break them because these loads are so large. And actually worse than break them, just deflect them a little bit so the shape doesn't come out as you want it. Because as Rick said, the number one thing you're ordering is the shape. It doesn't matter how pretty it is or how strong it is if it's the wrong shape. So getting the shape there is very important. So quickly here, let's look at a flat die tool stack. The top left, the pink piece with the green extrusion going through it, is the platen ring. That is physically part of the press. At the other end, the black and white section is the horseshoe. The horseshoe is where we put the die in the press. That's how we manipulate the die within the press to put it in place. The horseshoe is the same size as the die ring, and inside the die ring goes the die and the backer. And there is this little purple thing there called a feeder, which we sometimes use. The die and backer sit against the bolster, and that is the tool stack. And that tool stack has to withstand all of that load that's coming from the press and not deflect. So it's quite a challenge, but it's far from impossible. It's just one of those things we have to manage.
But if you take a look at the way this tooling is designed, the thing you notice is you have immense pressure on the front face, and then each part behind it gets bigger and bigger and bigger. And what that does is increase the amount of contact square inches so that this pressure can be dissipated out to the press at the very back end, because nothing will withstand direct 98,000 pounds per square inch pressure right on its face, and it'll push right through the same way that the live end of a bullet gets pushed out through a barrel on a gun. It's got to be dispersed, and the various square inches has to be increased so that we can dissipate it. And the interesting part is that even if you notice the pink part at the top left, it's built into the press, but it is even replaceable because eventually the stresses will get to it and it will cave a bit.
And it will coin. You'll get coining and damage to that surface. So the pressure ring can be removed and replaced, and that is an important part of the process. The next thing that comes into play is the effect of alloys. This graph here has got the common 6000 series alloys, from 6060 on the right through to the strongest, which is 6061. In fact, there's also 6082 as a possibility. It's even slightly stronger. The thing that's important to know is as that material gets stronger, which is going left, the extrudability is decreased. And this is a big issue because, as Rick says, as end customers, what you're buying is press time. And if the extrudability is decreased, then the product per hour is reduced and you end up renting more press time. So it's a direct cost. So I encourage you not to use things that are stronger than you need. I had someone recently contact me and ask me if I could help him make a seat rail for a car. A simple U-channel is 7075, which is a very, very strong alloy used for making the wing spars in aircraft. And I explained to him that a 6000 series alloy would extrude at several tens, if not hundreds of feet a minute, whereas 7075 would extrude at several inches per minute. And therefore, he would be paying for 100 to 150 times as much press time for his components. He then very quickly decided that 6061 was a much better alloy. So choosing your alloy wisely is important. Stronger alloys are harder to push. But the other thing here, which we haven't introduced so far, is that stronger alloys, when they come out of the press, they leave the press at about 1000 to 1040 degrees Fahrenheit. And for metallurgical reasons, for the strengthening of aluminum, it is important that they are quenched to 400 degrees Fahrenheit in under 1 minute. To do this, these stronger alloys like 6061 are pushed through a water bath. And it cools it down fast. You can hear the fizz as it goes in, and the section gets cooled tremendously. The problem is the fast quenching in that water bath causes strong distortions. So the stronger alloys are limited really to less complex shapes. If you want fine screw lugs and long, thin arms and nice things to make architectural shapes, some of these stronger alloys just can't be done because to get the strength, they have to be quenched in water, and quenching them in water will distort the shape. So it's a little bit of a cat chasing its own tail. Now here, you have a picture of a heat sink, 2 heat sinks in fact. And there are 2 elements to this. The first thing is the length of the legs. Try to imagine the steel die, which is the exact opposite of this image. There are long steel tongues with almost no support under enormous pressure. So making these dies is challenging. Imagine running those through water, you'd have all sorts of problems. Those legs would deform and it would just not work. So for alloys with complex shapes and high tongue ratios, our choice of alloys are really quite limited.
So when we talk about all these pressures and we're talking about varying alloys and varying strengths, and we want to talk about everything that goes on, the thing we have to remember is that these shapes must be extruded to tolerances that are about half the size of a human hair. Now, between flow variations, temperature changes, and deflection of tooling, we still have to be able to handle things like ±4 or ±6 thousandths of an inch. And that must be held over the complete length. So to do that, we have to support and keep the bearings as perpendicular to the front face die as possible. When you look at the components of the tool stack itself, what we have is the die, which is the original shape-forming mechanism for the extrusion. We have the backer, which we like to get up inside of the complicated tongues to prevent them from pushing through or breaking or distorting. And in some cases, we actually have the bolster, which we run tongues up in. Depending upon the shape, you'll notice that there's quite a variation of tooling costs involved. And again, that is because of the tooling requirements and based a lot off the aspect ratio of the tongues. If you take a look on the top or the left-hand side, you'll notice there's just a die plate, and because the tongue width is quite narrow, there isn't room for a backer. Now, when we get into discussion stages, that is perfectly all right as long as the depth of the tongue is not too long. In the next one, you'll see that the tongue has gotten wider. So now we can start to get a backer up in there. And if there's room on the next one, you'll see that we get a backer and a bolster in there. The more support we have, the more consistent the extrusion is over the length of over the length of the billet.
So what you're getting here is, if you ask for a very narrow, very long tongue, we can't put support into the die backer and we can't put it into the bolster. So that thin die plate on its own has to resist deflection on its own. So one of the most challenging things you can make in extrusion is a long, narrow tongue. So one of the things we're going to discuss here is how we can design that out of the die by changing shapes a little to get you what you need as an end customer, but to make it extrudable for us.
And I think the one thing we forget to mention every once in a while is the bearing does form the shape and control the velocity, but behind bearing there has to be some sort of clearance because this flow does not necessarily go straight at the beginning anyways, and if it touches the steel behind, the support steel within the die itself, it will adhere to that and simply plug the die and break, and that'll be the end of that particular piece of tooling. So the things we have to realize is that the longer the tongue, the more difficult the extrusion. The narrower the tongue makes it extremely difficult because once again, we can't get support up in there to protect or to satisfy the requirements for this 98,000 pounds per square inch. As we start to introduce cantilevered tongues, then not only do we get the direct caving in the extrusion direction, but we also tend to get twisting, which, as you can tell, the more you twist and bend, it's going to want to break quicker. So the idea is to try and keep the root of the tongue as wide as possible so that the depth does not get caught up and break the die itself.
What we're trying to do here is show you some things which small changes in the design can make the die much more extrudable. A much more extrudable die means more pounds per hour, which means to get your pounds, you've rented less press time, which means your costs go down. So this isn't just looking at that from an extruder's viewpoint, this is also looking at it from an extrusion customer viewpoint. Small changes in your section, and we're going to show you two in a few minutes, can actually increase the functionality that you want whilst making it easier to push. You can get a better product at a higher productivity with some of the tricks we want to show you. So the reason we're explaining this to you here is that we want you to understand the background of what we're going to tell you in a minute.
And when we start to measure success, a lot of things are possible, but when we start to get into these more complex today type of shapes, the word we'd like to get away from is improbable, because we want to satisfy everybody's necessities so that the component they want to manufacture is great, but at the same time, we get put into a situation where if it's a high probability of breakage, that means that it's not really a good idea for the long-term thing. And before we know it, we cannot supply consistently, because the worst call anybody hates to make is to call a customer and say, we got a 2-week delay while we get another complex die in here because that one broke.
And one of the things here in the bottom left, look at this section there. Imagine the piece of steel which is required to make the inside of the bottom left section. The problem you have there is the piece of steel which is holding this big area under pressure is that narrow root. There's a small narrow piece of steel there. The area that's taking the pressure is the big tongue inside it. So you have very little supporting a very large load, and there is a risk of it breaking. So let's look at a couple of other just general design principles. One of the things we really don't like, and you as customers shouldn't like, is excuse me, is sharp corners. Sharp corners they generate more heat in the extrusion process, so they get hotter faster, and they limit the productivity. The slight rounding of a corner, even just a little bit, will actually reduce the amount of heat being generated locally and allow the section to run faster, which means you're renting less press time.
And one of the things we have to realize we haven't brought out is that when a die is manufactured, the aperture is actually cut by a machine called a wire EDM machine. As you can tell, wire is a diameter and EDM is electrical discharge. So what happens is the profile is actually cut by this piece of wire. So when we call for a dead sharp corner, basically that would take a manual operation to clear that out, because the radius of the wire, which is only 6/8 thousandths of an inch, will actually stay there. But the truth is, the aluminum will extrude around that or on that corner. Whereas if we make a sharp corner, because of the frictional contact of the aluminum to the steel, it will actually freeze in that corner and actually set up and shear on itself. So you'll end up with a much bigger radius with actually making the corner sharp. So I would suggest when we're doing things, and if you recall earlier, Richard said about the snap fit on that one piece, when we get those small return legs where we want to snap into a corner, those corners should have a small radius included on them, because the gap that's required for the snap fit can actually become oversized just by adding this radius and the aluminum not filling in. But these are the things that it's critical that we all communicate. And this is where today's shapes are becoming more and more involved the engineering group from both the extruder and the end-use customer to make these products so that we can go hand in hand and everybody will be happy.
So before we get too far into that, though, which is actually, I think, the key part of what we're going to talk about, is if we get our communications right, I think everybody can be satisfied at the end of the day, and we can get an excellent product through teamwork. And we've got two examples coming up in a minute. But one more example here. Back to that heat sink we ran, and next to it I have a sketch of a section. What I'm showing you here are these streaks. You see the difference in color appearance of the aluminum? This is a facet of extrusion and extrusion dies. And I've spent a lot of years trying to fix this. This is the same thing as where we put a screw lug. If we put a screw lug behind a visible surface, we get problems. So in the right hand of these two sections, that streak on that surface would actually be a problem, because that's going to be visible. There's ways we can approach it, but in general, we end up reducing the productivity a little and increasing the complexity of the section when we deal with these things. One of the ways around this is, here's a section where the screw lug has been put on non-visible surfaces. The circle is the visible surface, and instead of putting the screw lug behind the visible surface, it's been put behind the non-visible, so the streaking doesn't matter. It's amazing the number of times I've spoken to customers over my years in the industry and said, do you really have to have that screw lug on that face? You can't put it on this one? And the customer says, no, it's fine, put it on there. And we greatly reduce scrap, which is waste, and waste is, of course, cost. So considering where you put screw lugs and legs is really important. And if you absolutely have to have the leg behind a visible surface, what you can do is use decorative lines. You see here what we've done inside this lower red circle is put 4 or 5 features into the extrusion, and these hide rather nicely those issues that are going on behind. So there's lots of things, but as Rick said, we have 45 minutes and we've eaten up quite a bit of that already. We'd like to give you 2 practical examples of things that have been done.
So here's an extrusion that comes in as a hollow with 2 mandrels and a fairly deep tongue. And as we look at it, the one on the left, what this says is that, number one, it's going to make the extrusion difficult because the large masses, the hole of the aluminum will want to go through the place of least resistance, which would be the large mass. With 98,000 pounds per square inch pressure, it can shift the mandrels up in the upward direction. But most importantly, what it says to me is that somebody is going to do some machining on this mass after they've received the extrusion. The question is why? We're going to be manufacturing a custom shape to satisfy the customer. So if perchance it happens to be a bolt head or a screw head that's going to go up in there, if you look on the right-hand side, you'll see that we've built the head for the bolter right inside of the extrusion. We've also balanced out the flow of the aluminum on any side of the mandrel. We've reduced the complexity quite a bit. And at the same time, we've made the cost of the material less because we've reduced the weight. And most extrusions are sold by the pound. So number one, we've reduced your cost, but number two, we've also made it so the extruder can have a better chance of delivering you good material all the time. If perchance the screw is more of a screw that has to go in vertically or instead of horizontally instead of vertically, we can put a screw detail in this way, whereas you can actually put a screw in through the cap into that screw lug. You get good contact around most of the shape, and the gap itself is the only place where the thread won't catch. And before you know it, we've reduced the weight. We've made the tongues easier, and we've made the functionality of the thing satisfy the customer. Now, at the same time, we can look at the next shape, and we can see that in this particular case, if nothing was going to happen there, we can simply take a cut out of the extrusion and simply reduce the mass by adding a channel there and having 2 small legs that can sit on whatever the base piece is that's required. Again, easier tongues, less chance of breakage, metal thickness is uniform all the way around, and before we know it, we have extrusion consistency, which leads to customer delight. Now, other options we have is we can increase the mandrel to get the weight all the same. It's still not necessarily the prettiest of extrusions, but I mean, it's still got hollow pricing, which the tooling's a bit more expensive. But certainly, as you can picture this material cooling, because of the consistency in the wall, it's going to cool straight. We're going to hold the tolerances over the long length, and before we know it, everybody will be happy and it'll do its job. Now, if we want to turn around and save this thing, instead of the one on the left, which is a hollow, what we can do is take a look at the true application and modify it as shown here. And now, not only have we made the extrusion better, but we've also reduced the tooling cost because now all of a sudden it's a hollow section. We can put a backer up inside of it to give it all the support it needs. We've really reduced the weight because we've taken a lot of the other metal out. And if that satisfies your needs, then everybody's happy because the extruder has a higher percentage of saleable material per billet, and the customer gets quite good tolerances and lower tooling costs. So these are the things that in today's shapes we have to start doing is bringing in the engineering group, and if need be, bring in any other experts in the field.
So there's a good example Rick's given, where communication between a die maker, extruder, and the customer can actually optimize the shape, reduce costs by increasing productivity, reduce costs by changing the die type, and reduce costs by changing the amount of aluminum present, but not in a way that's detrimental to either party. So this is a very good thing to do. Now let me show you very quickly another section. This one on the left would be a semi-hollow die. There's no way you could make that tongue. The little tiny root, which is sitting over here on the left-hand side, this little tiny root here, would never be strong enough to be able to support the pressure on this whole area. It would deflect and break in a heartbeat, just snap, it's gone. So we'd make it as a shut-off die. That means we're paying hollow die prices, but it also doesn't run very well. Shut-off dies, they're a little funny to run. Plus, when it gets on the table, if it gets cooled from one side more than another, or it gets handled a little roughly, keeping tolerances on that opening of that gap is going to be very, very tough, because that section, particularly when it's hot, will deform easily. So let's go to the one on the right. I've made it into a full tube and put what I assume is for a screw lug there to take the screw. It will take the screw just as well, but it will actually extrude better because it's a normal hollow die. It will give better shape stability because there is now something supporting that gap when it's on the table cooling and in handling, packaging, and transporting. Plus, when you put a screw in it, there's something for the screw to act against other than the spring of the entire loop. So it's a much better functional section, and it behaves better on the table. Now, I propose we can go one more step. I've made it so it takes a longer screw lug. Well, I can immediately see Rick across the table going, I just told you, you can't have longer tongues. But what I've done here is I've opened the gap up at the bottom. I've created a wider route for the tongue down in this area here. So the tongue is actually stronger than it was before and will sustain this extra length. And that's the case you can have if you want an extra longer bolt.
I think the thing we have to realize is that 80% of the problems come from 20% of the profiles. I think one of the things that really has to happen is if you're an extrusion customer and you have any input as to your shape design, arrange a visit to the extruder so you can see the process itself and see how much mass there is involved to produce these extrusions. But the most important thing we can do, and I really emphasize the word important, is that we get the customers to discuss what's going on with the salespeople and the internal group in the die shop. So that the discussions that should take place are between the die shop and engineering, sales, production people, and fabrication people. Those fabrication people may be within your facility, but let's point out all the probabilities and possibilities of future problems before we get into true production. There's no sense in saying, oh, we should have done that later. Let's do it now. Let's just satisfy everything up front. So if we look at conventional communication, we had the customer, we had production, and we had sales and shape design. And before we knew it, we were off to the races, and then we would have somebody calling saying, I can't have this mark in the exposed surface because that screw lug's there because it shows up after paint. Before we know we're having an argument. So as Richard says, why not have the discussion first, move the screw lug if possible off of that exposed surface, and then everybody is happier and blazes at the end, and before we know it, we have customer delight. Customer delight means that the extruder is happy too, and before you know it, we don't have any problems, and we just keep moving on. So if we want to look at the improved shaped triangle, and I like triangles, of course, most people who know me, you know, because there's one person talking and two people listening and there's no draw, somebody's going to win. But today we should have the customer and sales dealing with the die shop manager and the production managers so that we can highlight the possibilities of problems before they start. It is such an easy thing to do. The only thing it takes is time, and believe it or not, a couple of hours up front at the beginning is a lot better than hours and hours per day at the end.
I was once called into an extrusion plant to try to work out why they were losing their shirts making a particular product. And it was a huge volume, a huge, huge volume. And we analyzed the die. Several of us looked at the die, and we'd actually got a really complex element with some mandrels inside the die. And when we got to the end of the long story of investigating this, the extrusion plant salesperson had actually suggested it. But that complex set of mandrels was making it very difficult to extrude, which kept the productivity down and was really, really hurting the cost for everybody, customer and extruder. And it was a nightmare situation. Had we had the conversation Rick suggested, drawing in the die people at an early stage, everybody would have been very happy, and it wouldn't have ended up being quite the troublesome situation we had.
I think the things that we have to realize is both the customer and the extruder have to understand what's expected. Communication is the best way to do it. If the extruder knows what the end use is, then he can do his contribution. If the customer understands the impact of a small change and how much of a benefit it is to the extruder, then all of a sudden we're happy. And flexibility and the shape design can happen before it starts. If we catch it before there's any costs, then we can make it so that everybody's happy. And happy is the good word, because regardless of what we think, the most complex shape that we have today will be today's shape tomorrow. I'll hand you over to Richard with that.
What we're trying to do here is we couldn't in 45 or 50 minutes tell you all the tricks and tips for reducing die costs or for reducing this cost and to make things run faster. We want to give you just a flavor, really, of some of the challenges that are being faced every day when people are making sections that you design and ask for. We're just suggesting that if you can involve some of the engineering and die people at an early stage, you might end up with something which is actually better for a lower cost. And of course, that's good for everybody. We have to remember the disc of steel is under enormous force, and it's producing very tight tolerant products. Certain aspects of die designs are more challenging than others. Screw lugs and tongues are really amongst the toughest things. And when those tongues and screw lugs are inside a hollow, then of course it magnifies things up. Also, location of masses. That first example that Rick gave you where there was a large mass on the bottom. If there's more than a 5 or 6 to 1 difference in wall thickness, or maybe even a 10 to 1 difference in wall thickness, this can be very challenging for the way the metal flows. It can affect the extrudability of the section. So talking to die people and doing these few extra steps at the beginning often improve extrudability and reduce waste. And as we say here, eventually reduces frustration down the line when you don't get quite what you thought you wanted. What is it the saying? I wish I thought I heard what you thought you said. So communication can prevent that, and we can do things. So working together as a team can create unexpected benefits for both the customer and for the extruder, and create what Rick says, customer delight.
And it's kind of interesting. It's a lot like having a webinar and having the phone system go out about 2 minutes before you're supposed to be on the air. If you don't land on your feet, you're in trouble.
So we're just starting out with this picture saying, if you get it right, you can make some great stuff. This is the Lotus Elise. And the Lotus Elise actually has that little red circle. That is exposed aluminum extrusion in the Lotus Elise. There is more of it in there. And that's tight tolerance, tough stuff to make, and it's a tough product. But it's a great little car if you ever get a chance to drive one.
If you happen to have an extra $200,000, you could probably buy one.
It's not quite that bad, actually, but it's not a supercar. Okay. Anyway, with that, to all our listeners, thank you. I hope the audio has been satisfactory with the phone, and we hand you back over to Nancy.
Thank you, Richard and Rick, for an excellent presentation. Thank you so much. We do have time for a couple questions, and we're going to try and get as many as we can in here. As a reminder, if you have a question, select Q&A or chat from the toolbar and type your question in the dialog box. So our first question comes from Kyle. He wants to know, for hollow profiles, can you dictate where the weld channels can be located? Obviously, the shape dictates the location, but can those weld seams be moved for more aesthetic purposes?
Absolutely, but in most cases, yes. It's very dependent on the type of shape it is, because if it's a very wide and narrow shape, for example, that's using the complete horizontal center line of the billet, then it becomes very difficult. But I mean, anything can be done as long as the communication takes place. I mean, there's certain situations where no, you can't do it, but usually there's a way to work around it as long as we know what the issues are and how much you'd like it changed. But I mean, if we can't do it, there are ways we could introduce some of the decorative detail, or even as simple as just a V-groove in that particular area, or just some scalloping, whatever the case may be. But there are ways around to hide that weld.
And also, the location of the weld is a lot to do with the position of the ports in the die, and the position of the ports are there to balance the flow of aluminum. So if you're prepared to give a little on, say, a wall thickness here or a wall thickness there, or move a detail from one position to another, you can move the webs around to some extent. The problem comes, you don't have to have the webs in exactly a perfect position, but the further you move out from perfect, the more you disrupt the flow of the aluminum coming over the web, and the more you risk things appearing on the surface of the section, and you risk the potential for weakness in that area. So yes, you can move the webs, definitely, but you can move it even more if you're prepared to negotiate how you can move a little bit of a mass or a screw lug or a detail within the section. Communication is everything.
All right, great, thank you. Okay, this next question comes from Denise. Can you comment on the effect of die face distortion resulting in blistered material?
Blistered material usually is external to the die. It takes place by a worn container. It can be a worn dummy block. It can be numerous things, dirty face on the container. But very, very, very seldom would the die be the cause of blistering.
In fact, I'd reinforce that. I'd say I'll put an extra two verys into the very, very seldom. There cannot be blisters without there being oil or air or something to actually expand. So the root cause is always trapped air or oil getting in. The design of the die might make the design more susceptible to those blisters appearing in the surface and being visible.
The butt shear not taking a true clean cut on the front face of a hollow, for example, will leave space for air to be trapped in by the next billet. But again, that is not necessarily the die, but if it's a consistent thing in your operation, talking to the die maker, there are possibly ways that in the design itself that could be compensated for.
Okay, great. Let's see. From Mohammed, we've got, what does it take in terms of engineering man hours to come up with a good die design?
Rick, you make it.
I'm sorry, I don't mean this to sound facetious, but how long is a piece of string? It really depends on what we're dealing with. I don't think it necessarily takes that many man hours. I think it's a matter of once the possible defect is pointed out, It's taking a look at the application and how we can modify to come up with the best solution. It may not be perfect. There's probably an improvement.
I think one of the things that's interesting there, Mohammed, is that what we've been talking about here is how to reduce the complexity of the shape for the die, smaller tongues, locational screw lugs, and other such details. If you come with a very difficult section to extrude, it will obviously take longer to design the die. I've worked with a lot of die designers, and some of the simple flat dies, I've seen someone design in 30 minutes. Some of the more complex hollows I've seen sit on desks for days as people are passing ideas backwards and forwards. And this is why the theme in many ways of this webinar has been reducing the complexity of the section through understanding of the die is a key way to keep costs down. If you can deal with the die maker as part of this process, and he says to you, well, maybe if this tongue wasn't here, it was there, it would be a lot easier. You say, well, hell, that's okay. That's great. Then, of course, you've got a win-win situation.
Okay, and I'm going to have one last question because I think it feeds into something that you said, Richard, to me offline. We have a multi-hollow, this is from Stuart, we have a multi-hollow extrusion that tends to twist and collapse as it cools. Rules, guidelines, new webinar?
Oh, boy. That one's a little like trying to work out which member of the choir is singing off key. Twisting and behavior, twisting and collapsing can be many, many causes. Some of which have very simple solutions and some of which are relatively complex. One of the issues you can get on a cooling table is if you have two very different wall thicknesses, the thin wall cools really quite quickly, and the thick wall cools rather slowly. And this leads to a distortion at the end of the day, which can cause twisting and can cause it to lay strangely on the table. So I'd like to be able to give you an easy answer to that one, but it really is a multivariant problem which you need to get into.
Okay. And actually, I have one more question here because I had a question about this too. Robert asks, what is a shutoff die?
It's very, very similar to a hollow, except the mandrel and the die plate itself actually butt up against each other so that the tongue doesn't get the direct flow of pressure. It actually is a step type of situation.
Yeah. If you look at the screen now, it's just coming up. This would be made with a mandrel like a hollow die, only where the mouse is at the moment, if I can get it to appear, there it is, where the mouse is at the moment, this little piece, oh, why is my computer hating me so much today? Right, that little gap in there, to make that gap, we have contact between the mandrel and the die plate. And that's called a shutoff. The one on the right-hand side is a complete hollow. The one on the left-hand side is the hollow with part of the section shut off. The problem is you normally do that for very complicated shapes here. And the previous question was about things distorting on the table. You want something to distort on the table. That one on the left there is the king of all distorters. And that's why we suggest the improvement of making it not a shut-off die, but a normal hollow die. And then you don't have the problem with that gap opening and closing.
What happens on that die is the outside of the shape cools very quickly in the atmosphere, and the center portion of it retains all the heat, and the only place it can show any movement is in the gap.
All right, great. I think we're running out of time now. I think we're actually over time. So I'd like to thank you again for a great presentation, Rick and Richard. And for sharing this information with us. Thanks to Hydro Aluminum Metals, USA, and Exco Canada, as well as all of our members. If you can go to the next slide, please. All of our members for making this webinar series possible. Next slide, please. If you are looking for an extruder, go to our website at aec.org/find-extruder, and you can find an extruder in your area or who has the capabilities that you're searching for. The recording of today's webinar will be available online soon on the AEC website, and we'll send you a link once it's uploaded. The evaluation survey for this webinar will be sent to you following this presentation. Please share your comments with us. As I said, your input is very valuable and helps us in developing future webinars. Last slide. Be sure to visit our website at aec.org/webinars for more upcoming webinars on aluminum extrusion. The website also has information and resources on aluminum extrusion process, design and applications, technical information, and much more. So this concludes our webinar for today, and thank you so much for being with us. Bye-bye.